Hello and good day, everyone. Welcome to IEEE Symposium on Wireless Technology and Applications 2021. My name is Vincent Yong Kai Long from Wireless Communication Center, University Technology Malaysia. Now I'm going to present my title on Wideband MIMO antenna for smart flood monitoring system. This is the outline of my presentation. The introduction includes the antenna, the water level sensor, as well as the smart flood monitoring system, and what are the problem statement in the design of such system. What is the aim and the objective of our paper? The literature review, that is the design related from the previous work. Methodology as a form of flowchart will be shown to you. Results and discussion based on the simulation result from the CST. The conclusion of our paper, including the future works and references. Smart flood monitoring system is a system to track water levels using Internet of Things so that the impact of flooding on traffic congestion can be reduced. The two key requirements of the system are the antenna and the water level sensors. The antenna are capable of capturing and transmitting the electromagnetic wave to enable data to be sent to the user equipment to establish a communication. Whereas the water level sensor helps to indicate and measure the amount of water that flows in the river. This helps to provide the flood information to the public. Wideband MIMO antenna system need to cover the frequency range up to the current 5G band. So the problem statement here, number one, is to require multiband to cover large number of population on flood information. Number two, requires lowest latency to send flood information to the public in the shortest possible time. Number three is to require larger capacity to accommodate the huge number of Internet of Things connectivity. From the three key points here, underlined the three requirements, namely multiband, lowest latency, and larger capacity. So we propose a solution which is to design 5G antenna. Why 5G antenna? Is because 5G antenna provides higher speed and lower latency as compared to 4G. It also provides enhanced bandwidth suitable for this smart flood monitoring system. Therefore, we need to design the wideband MIMO antenna for smart flood monitoring system. The aim is to track the water levels and reduce the traffic congestion caused by flooding. The objective are to design and simulate wideband Singapore microstrip patch antenna at the operating frequency for 700 MHz and 3.5 GHz. This is for the 5G application. To design and simulate a wideband 4x4 MIMO microstrip patch antenna and to analyze the performance of our proposed MIMO antenna. Our antenna is based on the microstrip patch antenna. The microstrip patch antenna is a metallic patch placed on dielectric material and supported by ground plate. It is chosen because it is easily fabricated on printed circuit board. It is also most widely used antenna. The installation is very easy due to its low size, weight, and cost. The width of the microstrip antenna can be adjusted, can be varied, so that the value W can control the input impedance, bandwidth, and also the radiation pattern. The fitting technique we use is the microstrip feed line. It is the most preferred when it comes to a printed antenna on printed circuit boards. Needs an insert cut into the patch to ensure the impedance feed line match to the patch without needing an extra element. It provides reliability, easy fabrication, easy impedance matching, and provides more spurious radiation. This is our flowchart for our methodology. First, we start with literature review by collecting the articles and journals related to the wideband microstrip patch antenna design. Then we design the antenna based on the paper and also the journal. We design it on the CST simulation software to get the dimension and also the material so that we can simulate it and we can see the 3D design and also able to see other results. For example, the return loss, frequency covered, the bandwidth offered, and also the radiation pattern. Once we run the test and see the simulation result, we check whether our result is good enough for the system. Or if we do not get the good result, meaning that we need to continue to simulate until the result meet the antenna specification. So in the optimization process is considered as the simulation until the best result is obtained. Then next we can move on to design and simulate for wideband, multiple input, multiple output, microstrip patch antenna, requiring to add one by one the number of ports to the antenna. Then we simulate to see isolation. As we increase the number of ports, the new technique should be introduced to reduce or to improve the isolation among the ports for the feed line. Then we also add another optimization here. This includes the alternate design. We have different ground plane design. The first one is the French shepherd ground plane in the frame shape, adding an extra matching element, which is the L shepherd slot, L slots to the ground plane, and another design with a full ground plane to compare the two results and see which one align with the design specification of our antenna for the smart flood monitoring system. The design specifications are the operating frequency, whether the antenna operates at 700 MHz and 3.5 GHz for the 5G application. The return loss should be lower than -10 dB. The gain between 9 to 10 dBi with respect to the isotropic antenna. The targeted envelope correlation coefficient, which is the measurement for the MIMO antenna, should be less than 0.5. The microstrip substrate is an FR4 with a dielectric constant of 4.3, having a thickness H of 1.6 mm. This is the initial design of single port antenna. In this design, we introduced tapered cut at 4 corners. This design is used because it can help to enable multiple frequencies being created and also depended on the number of step cut. So the ground plane here is a partial ground, meaning that the ground plane only covers partial part of the substrate. So we look at the parameter, the width and length of the substrate is the same at 169.85 mm. The width of the patch is 103 mm. The length of the patch is 131.5 mm. The W1 is the width of the step cut at 44.03 mm. The length L1 is 28.7 mm. It's the length of the step cut. The LG is the ground length, which is 18 mm, whereas the WF and LF is 3 mm and 20 mm respectively. This is to fit the microstrip patch antenna using the SMA connector. This is the simulation result for single port antenna. We need to draw a line at -10 dB based on the -10 dB return loss characteristic, the design specification. Then we can see the graph achieve a band from 0.61504 GHz up to 1.3606 GHz, covering the 700 megahertz. We also slightly bend for the 3.5. The bandwidth is too small. The frequency range is far away from 3.5 GHz. Therefore, this result shows us that the wideband single port antenna is obtained only at 700 megahertz band. Then we propose a design, which is the initial design of MIMO antenna version 1. In this design, the steppered cut has been replaced with a straight cut. The straight cut is formed by increasing the number of steppered cut infinitely. Therefore, if until a point it reach a point that the number of step cut it becomes insignificant, meaning that it becomes very small, forming a line, a straight line. So therefore, this is called a straight cut at the corner of the patch. And also the ground plane from partial ground to frame shaped ground, adding the extra parasitic element of L slope at the corner of the ground. The width and length of the substrate remain unchanged, 169.85 mm. The width and length of the patch is 131.14 mm and 131.23 mm respectively. A represents the straight cut of the patch, diagonal cut with a distance of 60.6 mm. B represents the horizontal cut at 45.5 mm, and C is the vertical cut of the patch at 45.3 mm. WD is located here with 39.22 mm, and LD is 27 mm. So we simulate the MIMO antenna, comparing the straight lines with the step cut at the corner of the patch. Also, the ground plane has been replaced from partial ground to frame shaped ground and L slots. So we see that the frequency bandwidth is improved when the step cut are replaced with straight line. So based on the comparison, straight line has a better desired frequency bandwidth than the steppered cut, the initial single port antenna design. Now we move on to the second design of MIMO antenna version 2, also known as the final version of the proposed MIMO antenna. We are using the same technique from MIMO antenna version 1, straight cut, but we change the ground plane from the frame-shaped ground with the L slots with the full ground plane. And also the parameter, the variables has been changed. For example, the width and length of the patch reduced to 117.85 mm and 118 mm. The diagonal cut, the straight line, A is 54.41 mm. The horizontal cut is 41 mm, and lastly the C is vertical cut with 41.6 mm. So we compare the full ground plane result with the partial ground, and notice that the desired bandwidth for the system is achieved with full ground plane. This is the final simulated reflection coefficients of MIMO antenna system. All the S parameter can achieve the desired frequency range. So we covered 0.69792 to 0.72369 GHz for 700 MHz, as well as covering the 3.4198 GHz to 3.4809 GHz for the 3.5 GHz for 5G application. Other than that, we also have 1.6094 1.6362 GHz for other wireless applications, 2.0276 GHz for the UMTS application, and also the one frequency that is closer to 3.6 GHz at 3.6889 GHz. This is the current distribution of the MIMO antenna, showing with and without the effect of adding the L slots at 0.69 GHz. So A and C is port 1 excited, whereas B and D is port 3 excited. So here the ground plane is modified by introducing the 4 L slots at each corner. This is actually to enhance the isolation or improve the isolation between the ports. So we see that dimension slot with width of WD equal to 39.22 millimeter, and also the length LD is 27 millimeter. So what is the purpose of creating the slot? It's actually to reduce the coupling effect across the L corner of the ground, meaning that the current distribution more will be going into the main patch of our MIMO antenna. This will increase the energy to help our antenna able to transmit and capture the electromagnetic wave for communication. Although we added the LD, the length of the L slot, but we do not know the exact value of LD. Therefore, a parametric study on LD is shown to see how mutual coupling is affected by varying the LD from 10 to 27 millimeter. As we increase the LD from 10 millimeter to 27 millimeter, we notice that the isolation is improved from minus 34.06 dB to 45.43 dB. So therefore, the proposed LD, the length of LD is 27 millimeter. This is the simulated isolation of the MIMO antenna system. Each curve represents the isolation between two ports. Then the result here shown that good performance for 5G application with isolation greater than minus 10 dB for all ports except for isolation between port 1 and port 3. The desired frequency band is plotted from 0 to 4 GHz, and we notice that at the 0.7 and 3.5 GHz, the envelope correlation coefficient is less than 0.2. And also the value of diversity gain is about the 9 to 10 dB at 9.0323 and also 9.9971 dB within the entire desired band. This is the radiation pattern of our antenna. We can see that in the 690 MHz, almost bi-directional radiation, and also the directional radiation pattern with broad main lobe at 3.5 GHz has been achieved. This is the simulated maximum gain and also the simulated directivity of MIMO antenna. The result are for only port 1 and port 2 shown in this slide. The coverage frequency of simulated results are both the 0.7 and 3.5. So we put the marker at 0.7 GHz and 3.5 GHz to get the maximum gain of MIMO antenna system based on the simulation and also the activity of MIMO antenna based on the simulation. So here 0.72 GHz, we see a 5.012 dBi, and also 3.5 GHz, the gain is 6.8355 dBi, meaning that the maximum simulated gain achieved is between 5 to 6.8 dBi. The efficiency of the MIMO antenna can be calculated by maximum gain divided by the directivity of MIMO antenna. The efficiency here is 70 to 80%, which corresponds to our targeted efficiency for the system. In conclusion, the addition of frame-shaped ground and L slot can be used to reduce the coupling effect, but further optimization is still needed to be done to include the technology for the current design. The proposed wideband MIMO antenna, the simulated results show that all the ports provide 70% efficiency and a return loss at least -10 dB for the desired band for 5G application. The S parameters in terms of isolation is less than -10 dB at the expected frequency except for isolation between port 1 and port 3. The simulated envelope correlation coefficient, which is to determine the diversity performance of the MIMO antenna, shows that the broadband far field is less than 0.2 and the simulated diversity gains of about 9 to 10 dB are obtained. Based on the results from the simulation, the S parameter graph, simulated ECC, and also the simulated diversity as well as the radiation pattern characteristic. Our design is suitable for 5G usage for the smart flood monitoring system. The future works are further optimization on frame-shaped ground, including the current technology, and also for the new design. Increase the number of ports from 4 ports to 8 ports to see the difference, and also to further analyze the improvement of isolation. Fabricate the antenna and measure the performance of wideband MIMO antenna, whether it is the proposed design of our MIMO antenna will be fabricated and measured in the etching lab and the anechoic chamber. For more information, please visit this website wcc.utm.my or go to Facebook page at m.facebook.com/utmwcc/. This is all the references of our paper. That's all from my presentation. Thank you for your attention.